Let us continue with our design of different counter. And tomorrow we'll start with chapter number 4, that is Moore machines and Milli machines and special types of designs. Just a minute. I hope you can see my screen.
Yes, sir.
So last time we saw a simple counter, and what we'll do today is we'll see slightly different counters and see how we can change the timings or the sequence of counting, because you must have seen these lights, blinking LED lights. They blink in a certain sequence, and the sequence can be changed with the help of a controller. So precisely what I am trying to look at today is, so today's lab will be focused. We will be focused on two things. The first thing will be uh, different counting sequences. Uh, all circuits will be synchronous circuits. Synchronous means the clock will go simultaneously to all the flip-flops. And second, we will see a special type of counting which is called as shift register. Shift register. So in this, we will have serial in, serial out. Then we may have serial in, parallel out. Then we may have parallel in, parallel out. And then we have fourth one, that is parallel in, serial out. So when we combine all this into one big circuit, it is called as a universal shift register. Universal shift register. So many times in the exam they will ask you how a universal shift register works, and especially the diagram for the universal shift register. So if it is asked for 10 marks, like around 6 to 7 marks will be only for the diagram because it's huge. And explanation would be just 3 to 4 marks, not more than that. So today's lab will be focused on this different counting sequences and shift registers. So I'll be discussing the design of the counter, because what is important to me as a engineer is how to design things. And we will see some detailed designs, and based on those guidelines you can continue with the others, or something that is there in line with those designs. Okay, so let us start now. Today's first problem is, that is design a mod 6 up counter So this is the problem for today. Why is the options not coming? Just a minute. So let's go ahead with this thing. So this is the first question. Design a mod 6 up synchronous counter using a D flip-flop. So mod 6, as the word itself says, mod 6 means I want to know which are the states that it will count. Mod 6 means which are the states that it will count. Yes, which are the states that it will count? Okay, it should count from 0 to 5. It should count from 0 to 5. It should count up. The keywords are synchronous and using D flip flop. So this we can put it as D flip flop. So the number of flip flops, whichever flip flop it is, doesn't matter. It is going to be the same. So first step is calculation of number of flip flops using D flip flop. So here m is equal to 6. So the value of n for which this condition is true is going to be n equal to 3, and that is the reason why the number of flip flops are going to be 3. So just copy this quickly. So today I'm going to go design wise a little bit faster, but we will see more and more circuits. That is the objective. Okay, so let's go ahead. I hope there is nothing much to write in this thing because it's just a mod 6 up synchronous counter, but we have to see to it that my valid states are now 0, 1, 2, 3, 4 and 5. So I will count from 0, 0, 0 to 1, 0, 1. And after I reach 1, 0, 1, my next state should be again this thing. So that is my objective. So let's go ahead. So please write down the excitation table of the D flip-flop in terms of Qn and Qn plus 1, exactly similar to what we had done before in the previous sum. Yes, Asmita and Hemant, you have given the right answer. So quickly do all this. Even if you don't write the excitation table, it's fine. But as a procedure, we should have something in the front. So that is the reason why I just said let's have it. Okay. So let's go to step number 3. That is writing the excitation table. So let's look at the excitation table slightly in detail. So this is the present state is 0, 1, 2, 3, 4 and 5. And these last two entries are 6 and 7. But we are interested in counting only till 5, that is from 0 to 5. We are interested in counting only the first 6 states. That is the reason why if you look at this particular rows and columns here, this first is 0, 0, 0. The next state of that is going to be 1. This is 2, this is 3, this is 4 and this is 5. So the next state of 4 is 5, that is 101. But the next state of 5, I have defined it to 0. That means once I reach 5, the next state defined for 5 is 0. And that is the reason why we can count from 0 to 5. That is, the number of states will be 6. When you are using a D flip-flop, the D input is equal to the next state output. So you can see that this next state outputs and D flip-flops exactly are the same. On which basis am I saying this? Because D2, so you can find out the values of D2. You can find out the values of D2 based on the excitation table. So you can see, let's say if you want to calculate D2, then I will see here Q2 and Q2 plus 1. So based on whatever these combinations are, I will calculate the D2 column, then D1 column, and then D0 column. Please note the next state in this case for 6 and 7 is don't care. It is don't care. So basically you have defined the next state of 5 as 0. So the counter will go to 0. And what the next state for 6 and 7 is, we really don't care about it. It can be anything. So as a designer, if somebody asks me what is the next state of 6 and 7, or what should I keep the next state as 6 and 7, so I will just say keep anything. So that is the reason why I have written here don't care conditions. So please copy this excitation table, and once you are done with this, just write done in the chat box. So once you are done with this, just type done in the chat box. Yes, any doubts in this particular table, please ask. The problem with this kind of counter is it will count from 0 to 5, that is, it will count 6 states, that is not a problem. But there is one small problem that is called as lockout. There is one small problem called as lockout. Lockout means by chance, let's say by mistake, even for some time, if the counter goes in the sixth or seventh state, then the problem with these states are that its next state is not defined. The problem with the states 6 and 7 is that the next states are not defined. And that is the reason why the counter goes into an unwanted state. You can observe these conditions many times on the station. I have observed it that many times the station indicators, they show some value as FF, E, CD, something like that. So basically what has happened is that the display has gone in lockout, and the only way to bring it back is reset. So there has to be a program, or the design has to be such that the output does the counter never locks out. And that is the reason why instead of defining these last two don't care conditions, we can define them as 0, 0, 0. So that is quite possible. Okay, so have you copied this? Yes, somebody's microphone is unmuted. Who's this? Yes, so can we go ahead? So again, please note, is there any doubt in the defining of states? Please unmute and ask. So this is a mod 6 counter. Mod 6. Again, I am repeating, it will count from 0 to 5 and back from 5 to 0. So the next state of 0 is 1, 1 next state is 2, 2 next state is 3, 3 next state is 4, 4 next state is 5, and the next state of 5 is again back to 0. Okay, so let's go ahead. Now we want to find out, where we are designing the circuit, means we already know that there have to be 3 D flip-flops. We already now know that there have to be 3 D flip-flops. But what hardware I have to connect in between or before the flip-flop, that I don't know. So naturally I will use 3 K maps, one to find out D2, D1 and D0. Now D2 will depend upon Q2, Q1 and Q0. So basically these are 3 inputs. So we want a 3 variable K map. So 3 variable K map will have 2 raised to 3, that is 8 cells. And that is the reason why. Let's see now the calculation of D2. So if you look at D2, then the D2, these are the positions where D2 is 1, and the last two, that is, you should note this, 6 and 7, they are don't pairs. So this is 1 and this is 1. So very easily we can say that this is one pair and this is another pair. So there are 2 pairs, and the first pair will give me Q1, Q0, and the second pair will give me Q2, Q0 bar, Q2 and Q0 bar. So similarly, calculate for D1 and D0. Similarly, calculate for D1 and D0. And then with the help of DSCH, we will implement this on the editor. So keep your DSCH open. We will see the implementations. Karthik, can you hear me and see the screen properly?
Yes, sir.
So should I go to the next slide or people are still copying?
Yes, sir. I am still copying.
So don't, like I said, don't copy the first KMAP, only the second KMAP. That's it. I'm just closing the slide for 1 minute. Go ahead with D1 and D0 from the table. Go ahead with that. So can anybody post the answer for? Come on, do it. This was for D2. Let's see for D1. So for D1, the key map is like this. Again, 6 and 7 are don't pairs, and there are ones at 0, 0, 1 and 0, 1, 0. So here you can simply have one pair like this and one isolated cell. There is no pair possible. So here we'll have Q1, Q0 bar, and this is Q2 bar, Q1 bar, and Q0. So that is my B. Yes. I want people to similarly for D0. Okay, yes. So let's see D0. So here we have, okay, so D1 is correct. Yes. Bar, okay, Hemant. Let's see D0. Okay. D0 is Q0 bar, which is correct. So you will have just one quad, and quad will eliminate two variables. Only one is correct. Okay. So once this is done, so step number one is you have to calculate the number of flip-flops. Step number two is decide on the transition table of the flip-flop or the excitation table of the flip-flop. Then step three is create the transition table using the excitation table of the flip-flop. And then finally, step number four is calculating the K-maps of all the inputs of the flip-flop. And then finally is the implementation. So this is going to be the implementation of the flip-flop. So what you will do is first you will take these three flip-flops. You will get QN bar. So take two lines down here. Then you will create the hardware here. So this is for D2, this is for D1, and this is D0. So D0 you can see this is my flip-flop D0, this is D1, and this is D2. So here we have simply Q0 bar. Something like that. So, and the outputs are connected to the LEDs just for simulation sake. I have done that. In the exam, if you don't show this, it's fine. But anyways, here we are interested in simulation. So I'll just open the simulator and you can copy it from the simulator directly. So let's see synchronous mod 6 counter. So the circuit is already there in front of you. And let's see the working of this. I'm just simulating this thing. You can see initially I have to reset the flip-flop. So first I'll put a reset, and now you can see here on the display below, it will go to 3, 4, 5, and after 5 it will become 0. Again 1, it will count like that. So start building this circuit quickly. Yes, any doubt in this, please ask me. Even in the implementations, if there are doubts, please ask me. So are you all able to see that the counter is counting from 0 to 5? Can somebody unmute and confirm that? On your screen, you should be able to
Yes,
see
sir.
that the counter is counting from 0 to 5. So this design is absolutely perfect. So you can see 3 and 4 and 0, 1. So this will slightly go to, and 3 is getting skipped 4, 5, and then 0. Yes. That 6 got skipped because of some latency. So you can see how the counter is running. And so you can see some hardware which is there in front of you. Now the problem is, so what you will do now is those who have done with the design, those who are implementing fine, you can just continue implementing the designs. And those who are unable to simulate this thing because of device restrictions, what you can do is you can start designing same circuit again, that is mod 6 but lock free. Mod 6 but lock free. Lock free means for 6 and 7 we have written don't care conditions in the transition table. So instead of don't care conditions in step 3, we will put zeros there, so that even by chance if circuit enters 6, the next state for it is defined to 0, that is it will go to reset. By chance if it goes to 7, then still the next state for it is again 0, so again the counter will reset. So even if the counter goes into a wrong state, we should be able to bring it back to one of the valid states. Now you may ask me why only 0, why not 1? You can choose any one of the valid. You can, for a mod 6 counter, the valid states are 0, 1, 2, 3, 4, and 5, and the invalid states are 6 and 7. So the next state in the lock-free counter for 6 and 7 can be any one of the valid states from 0 to 5. Not necessarily it has to be 0, 0, 0 only. But generally, if something goes wrong, we would want to count again. Generally, if something goes wrong, we would want to count again. So that is something that we want to do. So generally you can see in a printer when you give a command to print the pages. Let's say that you are trying to print from 1 to 10 pages. And by mistake the paper or something gets jammed. So the counter, let us say, got jammed at 6 or 7. So it has to again start printing because it doesn't know whether which pages are printed correctly or not. So once you press one button on the printer again starts printing from page number 1. But this also has got some disadvantages because if the number of pages that you are printing are 100 or 100 and 200 pages, and if some error comes in between, and if the printer starts printing from page number 1 again, so 100 pages might get wasted. So there are solutions to all these problems, but we are discussing a very preliminary one. So as we progress, we will discuss about it. But this is how the counter gets simulated. So variety of applications counters are used, and this is just one of them. Now, if somebody asks you to design a mod 7 counter, that counter will count from 0 to 7 and 0 to 6, sorry. 7 will be the invalid state. So accordingly, we can have transition tables and design the whole. Yes, anybody, any doubt, please unmute and ask. I am waiting for some doubts from your side. Come on, you start with a lock-free counter. You can start with a lock-free counter. Also note the LEDs down there, okay? LEDs indicate the values. Q2 is the MSB and Q0 is the LSB. Q2 is the MSB and Q0 is the LSB. So you have to read the LED from right to left, not left to right. So this is the implementation. And one of the most important things is state diagram. So let us see how the state diagram looks. So state diagram will look this way. You can see state six and 7 are not there in the diagram. State 6 and 7 are not there because you don't care what they are. Their next state is not defined. So you cannot show 6 and 7. Why we cannot show 6 and 7? Because we do not know what is the next state of 6 and 7. For example, the next state of 0 is 1. The next state of 3 is 4. The next state of 4 is 5. The next state of 5 is 0. It is not 6. So the next state of 6 and 7 are not defined. That is the reason why we cannot show state 6 and 7 in the state diagram. So the next problem would be something like this. So let us discuss more on the lockout condition. Mod 6 counter, the valid states are 0 to 5. The invalid states are 6 and 7. Just now we saw that. By mistake means anything can cause this mistake. For example, if there is an overcurrent or if there is some timing issue, then we can go in state 6 and 7. So by chance, if the counter goes in the state of 6 and 7, then the output of the counter will not change, because the next state of 6 and 7 are not defined for the counter, and this condition is known as lockout. So lockout condition is related to the invalid states. The lockout condition is related to the invalid states. It is not related to the valid states. So invalid states can cause this problem, and that is the reason why we try to define the next state of invalid states. The lockout condition occurs when the next state of all the present states of the counter are not properly defined. Not properly defined meaning some are don't care. Some are don't care. In order to avoid this condition, the next state of each unused state, in the counter can be initialized to 0. As a default, we again initialize it to 0. Not necessarily I told you it has to be 0, but yes, we start counting again. Initializing to 0 means if something goes wrong, count again. It is that way. So if I give you like 100 1 rupee coins and I tell you to count, and you are counting, and suddenly in between somebody comes and talks with you and you lose the count. So what you do? You start counting again because you lost track of your previous count. So when we lose track of our previous count, we start counting again. Do you start, let us say you are counting from 1 to 100. Somebody comes and disturbs you when you are at 46. You lost that count in your mind of 46. So you don't start counting again from 20. You start counting from 0, just to be sure that the count is correct. So what we do actually, and we expect the machines designed by us to do the same, and that is why it is generally like that. But if you want to create some problems in the design, you can still do it. So this was something about lockout. So what this condition actually reflects, how this condition actually reflects in a problem. So again here, just to be flip-flop. So here in the exam, they may ask you mod 6 lock-free synchronous counter using. So all other specs are same. So again, M is 6 and the number of flip-flops N is equal to 3, and you can see 6 is less than 8. So that is the reason why the value of N for which this condition gets satisfied is N equal to 3. But now what is important to us is lock-free. So where in the design I will account for lock-free? So that is in step number 3. In step 3, I will account for this lock. So step 1 is similar 10. We have step number 2. So we are again using which flip-flop? D flip-flop. So the excitation table of D flip-flop is a standard. This is standard. So it will also remain the same. So once you do this, step number 3, I will wait for some time because here now you should again observe here the changes. So you can see here this is 0, 1, 2, 3, 4, 5. This is 6 and 7. We are expecting our counter, mod 6 counter, to count only from 0 to 5. Only from 0 to 5. So the valid states are 0, 1, 2, 3, 4 and 5. Now you can see the next state of the valid states, that is from 0 to 5. Here this is 1. The next state of 0 is 1. The next state of 1 is 2. Next state of 2 is 3. Next state of 3 is 4. Next state of 4 is 5. Next state of 5 is 0. So next state of 5 is 0. That means in regular sense, if there are no errors, the counter will count like the previous one. But now you can see here in these states, here, this and this, there are no don't cares. So what we have defined is, we have defined the next state of the invalid states also. So these are valid and these are invalid. So for the invalid states, the next state is now defined to 0 purposely. It is now defined to 0. So previous excitation table wise and this table wise, your transition tables are slightly different, meaning the don't cares have been replaced by zeros. So now with this table, I want you to design for D2, D1 and D0. Your K-map will now become complicated, or you will get more number of terms because you previously you had don't cares, and don't cares you could assume as 1 and 0 as per your convenience. But now that don't cares have been replaced by 0 states, which reduces the number of ones. When the number of ones reduces, the possibility of getting a quad or an octave reduces and we get isolated cells or pairs. So when the reduction is less, we will get more hardware. So that is the reason why when we try to that is at the expense of additional hardware. So when you see don't cares in the truth tables or in the excitation table or even in the transition tables, you should see that okay, my hardware will be less. But if there are no don't cares, then the hardware will be more, but the circuit will be more robust. It will be error free, it will be fast, it will be everything will be there good, but at the expense of additional hardware. So I want you all now to calculate the K-maps for D2, D1 and D0. So D2 will be in terms of Q2, Q1, Q0. D1 will be in terms of again the present states, and D0 will also be again in terms of the present states. So please calculate this thing and tell me the answer. I am keeping this table as it is. Any doubts, please ask. And it is interesting to see the state diagram of this counter, because now 6 and 7's next state have been defined.
So can you please present the previous slide for 1 second?
It is the excitation table of D flip-flop only, Vishwas.
So now the question of lock free.
So I will tell you the question.
Okay, sorry.
Design a mod
Design
6 lock-free counter.
mod
Design a
6.
mod 6 lock-free synchronous counter using D flip-flop.
ओके ओके सर, बाकी सब तो सेम रहेगा ना, बस वो डोंट केयर के अलावा के जगह पे
हाँ.
0 आएंगे.
Yes, as
ओके
you can see on the screen, step number 1 and 2 will be exactly the same.
यस सर.
So now don't care has been replaced by 0. So K-maps will change. So at least do the design. Implementation can happen anytime. I will show you the implementation. Implementation you can do it later on. But I am slightly more interested on the design part of it. Because once you have the equations for D2, D1 and D0, it is just drag and drop in the simulator. So once you are done with this, just write the correct answers in the chat box. I am looking for the answers for D2, D1 and D0. Okay, I am waiting for the I'm just correcting a few things in the meantime. Okay, I'm waiting for your answers. So let's see the calculation of D2. Now see the positions of 6 and 7 specifically. See the positions of 6 and 7. They have become 0 and 0. So we are having zeros, all zeros. So that is the reason why now we are getting isolated cells. Isolated cells means more reductions. More reductions means more hardware. So you can see that we get two isolated cells, and these are the two values. And D2 will be addition of these two. So next is D1. So for D1, again here we are having a 1 here and here, 1 and 2. So again we have two isolated cells. So D1 will be as given here. So this will be D1. Okay. So these terms are very huge. So if you are typing this, you can just save it also, unmute and save D0. What will be D0? So these are the places where D0 is 1. So you can see that you can have two pairs. One is like this, the second one is this way. So can somebody tell me what is D0? Can somebody tell me what is D0? It should be Q1 bar Q0, and it should be Q2 bar Q0 bar. So that is this Q2 bar Q0 bar. This is Q1 bar Q0 bar, and that is P0. So anyways, I'm going to send you the slides. So you may note down only this term with respect to implementation, because today is a lab session, so I want you to implement, but without the design it's difficult to implement. So now you have D1, D2, D1 and D0. So implement this using flip-flops. And the flip-flop that is used is D flip-flop. Now just imagine that if they would have told us to do this using JK, we would have got lesser number of terms, no doubt, because JNK, the excitation table of JNK itself has got many don't care conditions. And but the problem is that here you are only calculating D2, D1 and D0. So in all you are calculating 3 inputs of the 3 D flip-flops. But JK flip-flop, each JK flip-flop will have 2 inputs. So in a way you are calculating 6 KMs. So design time is more, but you might get little bit of reduced hardware. That is quite possible. So that is why many times JK flip-flops are preferred over D flip-flops or for reducing the hardware, but the design complexity is slightly more with JK. D is simple. Whatever is in Q2 plus, Q1 plus, and Q0 plus. Exactly the same thing you can copy in D2, D1, and D0 transition table. So there we get something. Otherwise, we have to calculate D2, D1, and D0. Sorry, J1, K1, J2, K2, and J0, K0 from the transition tables. Okay. So the implementation of this counter is this way. So what you can see here is that this is D2, D1, and D0. So previously D0 was just Q0 bar previously. But now you can see D0 is something pretty complex. So what did actually happen? To prevent lockout condition, we require some additional hardware, some additional. So that is the moral of the story. Now let's see. Now this counter should also count from 0 to 5 only. So we should be able to see the same thing, but now we have account for the lockout condition. So I will just go back to the simulator. Let me open synchronous mod 6 lock free. So now you can see I'm just resetting this. It should again count from 2, 4, then 5, and then it will go back to 0. So you can see that the counter counts. So what I have used is 3 D flip-flops, and the hardware that I designed for D0, D1, and D2. Yash, are you able to see the counter count?
Yes, sir.
Now, why to count up only? That is the question. Why not to count reverse? 7, 6, 5. Or I want to count both up and down. So the next one I think is going to be up down counter using some mode control. So I don't know when the nowadays traffic signals come with one manual button. So if there are pedestrians who want to cross the road and there is heavy traffic, so pedestrian can press one button and the signals will become red immediately after some time, and you can cross and then the cars can go. So these functionalities have to be there in the counter, so that the count can stop for some time, again it can start. So such features are there. Now you can time the operations using you can have 3 approaches to the same problem. So let's say the problem is a traffic light signal control at a crisscross junction where there are 4 roads. So you can solve the same problem using a microprocessor circuit, but it will be slightly difficult because the microprocessor number of pins that a microprocessor has input and output pins. There is a slight restriction on them. You can increase the number of pins by using some kind of a IO controller, but then again you need to design the PCB for that, and which is going to be design wise slightly difficult. Then we have a second approach, that is using a FPGA. So you can just program this hardware on a field programmable gate array using Verilog or VHDL programming, and you can get the functionality. Now the advantage here is FPGA is not only high speed, it will be like around 20 times more faster than a microprocessor, and it will have many number of pins and many inputs and many output pins. So it is much faster. And the third approach is using PLC control, that is programmable logic controllers. So there also you can use a PLC to actually program something, but the programming there is called as PLC programming, and it is done using something called as ladder diagrams. So as you progress in the course, the same problem can be solved using three different approaches. The approach that you can take from this course is the Verilog or VHDL approach. Yes, yes, I think your microphone is unmuted. Sanchit, your microphone is unmuted. Please unmute. Please mute it. Do you want to ask something, Sanchit? Sanchit Deshpande. Sanchit, can you hear us? Karthik, Sanchit Deshpande is from which class?
Yes, sir.
Division A or B?
B.
Okay, so please call up the CI after the lab and tell Sanchit to call me.
Okay, sir. I will tell her.
So yes, meanwhile you all can implement this thing. So I will give you another 5-6 minutes to do this. Once you are done with this, just type done in the chat. The flip-flop part of it, you can do it very fast, but while implementing that, these AND gates you can see on the screen. So sometimes we make mistakes in connecting the inputs to the Q0, Q1 and Q2 terminals. So there you be very careful. And if anybody has a doubt, you can unmute and ask. Vishwas, are you following this?
Yes, sir.
So here what has happened is, because you introduced those zeros, your hardware has slightly increased. You can see that there are more 3 input AND gates. In the previous circuit, we had 2 input AND gates. So I think you all can design this. I'm just posting the codes in our screen. So I've just uploaded the files for your reference. So just in case if you go wrong, you can just take the schematic files and simulate it at your end and check. So out of this circuit, if you just closely look, we have seen the operation of gates, and I have also shown you how to design flip-flops. So inside the flip-flop also there are gates only. So everything is gates, and the number of gates decide the level of integration. So this counters will generally come in something called as MSI, that is medium scale integration. And if the number of bits in a counter increases, like for example, if this is just a 3-bit counter. So if there is a 64-bit counter, then that would come in LSI, that is large scale integration. So if you have implemented this, post the figures in the chat box. I'm just confirming, Karthik or Yash, can you confirm whether the files you can download or not?
Yes, sir. We can download it.
Okay. Okay, so let's go to the next implementation. So I have given you the implementation of the next counter, that is up down counter, up down counter. So let's look at that. Now before we go to the up down counter, let's see that here what we did is we defined the invalid states also, that is this 7 and 6 were invalid states, whereas 0, 1, 2, 3, 4 and 5 are valid. So the next state of 0 is 1, the next state of 1 is 2, the next state of 2 is 3, the next state of 3 is 4, the next state of 4 is 5, and the next state of 5 is 0. But now the next states of 6 and 7 are also defined to 0 and 0. That is why we show 6 and 7. So for a lock free counter, invalid states are also present in state diagram. Invalid states are also present in state diagram. Some books will write this as 0, 0, 0. They will write this as 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0. So it depends, but I think they mean the same thing. So draw the state diagram. Very important. And especially 6 and 7 are also present in this state diagram. So many times in the exam, they may give you a state diagram, and then they may tell you design a counter for this. The counter should count in this fashion. So immediately by looking at this counter, you should recognize that okay, that there are 8 states. Out of 8 states, which are the 8 states? That is 0 to 7. Out of these, which states are invalid? 7 and 6. Are the next states defined? Yes. Are the next states defined for the invalid states? Yes. So in that sense, you by looking at this state diagram, you can say that this diagram is a diagram of a lock-free counter. So in a GATE exam, they may give you this diagram and they may ask you a question like this, that the above state diagram considers the lock-free condition true or false. So the answer is true. And in your IA also you will get such questions whenever it happens. Okay, so let's go to the next. Design a mod 6. Now same thing, design a mod 6, but this time we are designing a mod 6 up as well as down counter, synchronous one, using D flip. Using D. This JK can be made by shorting inputs. Not shorting, sorry, putting a NOT gate. But anyways, we are directly using a D flip. So step number 1, absolutely same. Step number 2 will also be absolutely same. But now we want to count up as well as down. Please copy the question. Design a mod 6 up down counter. So for this up down operation, we have to these up and down are modes of operation, up counting or down counting. So we will define one more input, that is n. We will define one more input, that is n. So let us say that if n is equal to 0, for this namesake, I will count from 0 to 5, and when n is 1, I will count from 5 to 0, reverse. You can also keep this as 1 and this as 0, but either ways it should happen. You may say that why m equal to 0 only up count, why not 1? Okay, fine, do what you want. You are the designer. As long as you are able to do it, I don't have any objections. Okay. Step number 2 will also be exactly the same. That is the excitation table of the D flip-flop. That is the excitation table of the D flip-flop. You can see that the excitation table has appeared and it's exactly the same. There is no novelty in step number 2, but just as a design procedure I am putting it down. And step number 3 is where the real explanation lies. So let's look at that. Now I'm going to explain this thing in detail. Let's look at certain things. Now you can see that I have defined one additional input, M, and I am calling it as mode. You can see that. Then the next 3 inputs are my present state inputs. So in all, M can be 0 or M can be 1. Present state inputs can be Q2, Q1 and Q0. So it can be 0 to 7 for M equal to 0, and Q2, Q1, Q0 can be 0 to 7 again for M equal to 1. These are my next state inputs, Q2 plus 1 and Q1 plus 1, and then we have Q0 plus. So from where did we get this thing? From where did we get Q2, Q1 and Q0? We got this from the transition table. We got this from the transition table. So that is what it is. Now you can see here, I have divided the table into 2 parts. I have divided the table into 2 parts. So that red line indicates that division. Now you can see here very well that M can be 0 or M can be 1. So the present state can be, this is 0, 1, 2, 3, 4, 5, 6 and 7. And this is also 0, 1, 2, 3, 4, 5, 6 and 7. Now you can see here, when M is equal to 0, we are planning to count up, and when M equal to 1, we are planning to count down. So when we say up counting, you can see 0 next state is going to be 1, 1 next state will be 2, 2 next state will be 3, 3 next state will be 4, this will be 5, and the next state of 5 would be 0. So you can see that this is 0, 0, 0. Now I have written here don't care condition. That means, simply speaking, this is not a lock-free counter, but I say, okay, my frequency is less, so the probability that it would go in 6 and 7 is very low, and so I don't care about it. Okay. So to start with, we are not defining 6 and 7. We are saying that 6 and 7 are don't cares. I have also shown you that you can replace these don't cares by 0. Simply speaking, you will get a different KMAP. Nothing more than that. Just a new KMAP. That's it. Similarly, now if you look at the other part of the table, that is below the red line. So the present state, if it is 0, 0, the next state should be 5. That means I want to count up. So my next state will be 5. Sorry, down. If I am at 1, my next state should be 0, 1 less. If I am at 2, then my next state should be 1. If I am at 3, my next state should be 2. If I am at 4, my next state should be 3. If I am at 5, my next state should be 4. And if I am at 0, my next state should be 5. That means you don't have -1. Instead of that, you say you go to 5. And like I said, again, 6 and 7 conditions, these conditions are going to be don't care. So here, while up counting as well as down counting, we are not using the states 6 and 7. So 6 and 7 we have put here don't cares. So maybe afterwards you can design a lot of free counter just by replacing don't cares by zeros. That's it. Now you can see that D2, D1 and D0, D2, D1 and D0, just because we are using a D flip-flop, will be exactly equal to Q2 plus Q1 plus and Q0 plus respectively. That is, D2 will be equal to Q2 plus, D1 will be equal to Q1 plus, D0 will be equal to Q0 plus. Simply speaking that way. Now, D2 depends on M, Q2, Q1 and Q0. D2 depends on M, Q2, Q1 and Q0. Similarly, D1 will also depend on M, Q2, Q1 and Q0. And D0 will also depend on M, Q2, Q1 and Q0. So each of the inputs of the flip-flops, that is D2, D1 and D0, will depend on four variables, that is M, Q2, Q1 and Q0. That is why now we have to use a four variable K-map for D2, D1 and D0 each. And D2 we will get one equation, D1 one equation and D0 another equation. So please copy this table and start solving for the four variable K-map. So two inputs will be M and Q2, and on the other side you can write Q1 and Q0 and start filling the K-map. Okay, so first write this table and start filling the K-map. Any doubts in this particular table, please unmute and ask.
Hello, sir.
Yes.
Sir, for down counter, why 5 is written at the top?
Down counter, sorry, I could not get it.
Sir, for down, M
For
M is for M is equal to 1.
ah,
Huh. So my doubt is why 5 is written at the top, like in next state.
okay. So I will just tell you this. Down counting means if I am at 5, I will go to 4. If I am at 4, I will go to 3. If I am at 3, I will go to 1. If I am at 1, I will go to 0. If I am at 0, where will I go? I have to go to 5. So for a up counter, the reset is at 0, 0, 0. But for a down counter, the reset is at max value. Understood?
Okay,
this?
okay, sir. Got it.
It's like a
Yes, sir.
signal. See, it's like a signal. The green signal will count down, right? Let's say the signal is for 30 seconds. So it will count down from 30 to 29 and so on up to 0. At 0, the signal will become red. And it will not be, green will not be permanently at 0. No? It will not be permanently red. There will be one counter for red also. Once that becomes 0, the green counter will again be reset to 30. Got it?
Yes, sir.
So please ask the doubts. This is a good doubt. I was expecting this. Up is easy to understand, but what down is, down may have this doubt. So now you solve the K-map, which is going to be obviously huge because now we have 4 variables and you have to fill a 4 variable K-map. So if you have copied this table, I can go to the K-map part of it. Should I go to the K-map part of it? Okay, I'll go to the K-map part of it. Karthik, Anushka, have you copied this? Shubham?
Yes, sir. Yes, sir.
Start solving for D2, D1 and D0. So I'm going to the K-map of the first one, that is D2. These are zeros. So it's a 4 variable K-map and your D2 will be filled like this. So it is important to understand that 7 and 6 are don't care and 14 and 15, which were the last 2 states during down counting, are also don't care. The other ones and zeros will come from the other values. But 7 and 6 and 14 and 15 will always be don't cares in all the 3 K maps, that is for D2, D1 and D0. So here you should be able to get, this is one pair, this is another pair, this is another pair, and this is isolated set. So though you may feel that ones are there, they are very close, but you can see that no quad is possible, only pairs are possible, and just one isolated set. So there are 3 pairs and one isolated set. So this is M bar Q2 Q0 bar, which is MQ2 Q0. This is M bar Q1 Q0. And this is MQ2 bar Q1 bar Q0 bar. So D2 would be such a big thing. So can you see that when you want more functionality, please understand this word functionality. That means now you are trying to put more control up and down in one circuit itself. You require more hardware. And when you want to put more hardware, you will require more area. And that could be a constraint many times. So the plan is to reduce the area is to make each and every transistor smaller. So in EDC, you must be learning 3 types of transistor. Number 1 would be BJT, bipolar junction transistor. Number 2 would be JFET, that is junction field effect transistor. And the third one is MOSFET, metal oxide semiconductor field effect transistor. So out of these 3 transistors, the only person who is ready to become small without change in the input and output characteristics is the MOSFET. And that is why MOSFET is something that you should learn in detail, and that is what is actually used in the implementation of gates and many other things. So please focus all your efforts on MOSFET. And yes, BJTs are also used in slightly high power applications. So we have two technologies defined on this part. One is called as TTL and the other one is called as CMOS. So TTL means transistor logic, where we use BJTs, and CMOS means we use MOSFETs, that is complementary MOSFETs, that is NMOS as well as CMOS. And these are used to implement logic gates. So in chapter number 5, there is a small glimpse of what is TTL and CMOS. Anyways, it's very simple. But so chapter number 1, 2, 3, 4 are highly conceptual. 5 and 6 are just theory. Those 6 talks about programming, but exam wise it is theory only. Otherwise, chapter number 6 is endless because it is an introduction to Verilog programming, and any programming is endless only. You require a lifetime to learn a programming. Okay. So let's go to the calculation of D1. Yes. Can somebody unmute and tell me what would be the, at which positions you will have ones? So I know 7, 6, 14 and 15 I don't care. Which other positions you will get zeros and ones?
Sir, positions of 1 are 12.
1, 1,
Yeah, 1, then 12,
12,
2,
2,
and 11.
and 11 are ones. All others are zeros. Check it correctly.
Yes, sir, all other are zeros.
Okay, so let's see whether you are right or wrong. Yes, you are perfectly correct. Perfect. So now you make quads and pairs and whatever you like. Again, you can see that quads are not possible, but pairs are. And so this is what you get. Isolated cell will give you 4 terms. This will give you 3 terms, again 3 terms and 3 terms. So this is D1. Please copy this and also solve for D0. Also solve for D0 and implement the whole thing in DSCH. Now you can see you will face a lot of trouble in implementing this 4 input term. So this term, how will you implement this 4 input term? There is no 4 input gate in DSCH. We don't have 4 input NAND and in DSCH. So what you will do is you will take two input AND gates and connect it to another 2 input AND gate. So this is a 4 input AND. So this is what you will do in DSH. Here directly you can use a 3 input AND, 3 input AND. But here we don't have a 4 input AND. So either we have a 5 input AND or we can use a 2 input AND gates to do this. Come on. Design for D0. So D0 you will do on your own. So copy only the second k mega, not the first one, in which I have scribbled. Don't copy that. So calculating this only is important. If you go wrong here, then they're gone. So let's go to the calculation of B0. So again, 7, 6, 14, 15 are don't care. 7, 6, 14 and 15 are don't care. And which other terms are 1? Can anybody tell me? Yes, can anyone tell me the places where you will get ones for D0?
Sir, position number 0, 4, 12, and 8 are 1, and
0,
2
4,
and 10 are also 1.
12 and 8 are 1, and 2 and 10 are also 1. So naturally you can see that there is one octave, right? So there is one octave, simply 30 bar. So the calculation of D0 is not at all big, it is very small. So D0 is equal to Q0 bar. Now implement. Now implement this. You will require 3 flip-flops. So how will you implement this thing? Okay, let's see the circuit. So you can now see these 3 flip-flops are all in place. Now there is one additional terminal, that is mode. So this is mode. We are generating M and M bar, and then this is 0, 1 and 2. This is my B2, B1 and B0, and these connections are for those groups. So you can see here this this is a 4 input AND. This is how you can implement the 4 input AND gate. That is by using 2 input AND gates. And this is 3 input AND gates are already available in DSC. So let's see the implementation of all this. So first thing is I will reset. So I have already sent you the code for this. So you can simply open in DSCH. So first I will reset, make it 1 and then immediately make it 0. I will immediately make it 0. Now by default you can see mode is 0 only. So it will start counting up. The moment you reset, it will start counting up. After 5 it becomes 0. You can see in the corner that after 5 it becomes 0. Yes. It counts from 0 to 5. After 5 it becomes 0. So currently it is counting up. Currently it is counting up. Now if you want that this should count down, then I will make mode is equal to 1. I will make mode is equal to 1. Now you can see it is counting down. 5, then 4, then 3, 2, then 1, then 0, and after 0, 5. Anusha, can you see that your question is getting addressed here? After 0, it should again go to 5. That is why the next state of 0 should be 5 while down counting. Did you get that? Okay, Shubham, are you able to see this up counting and down counting? Now again I am making the mode 1. You can see it should start counting up. So this is the working of the counter. Up as well as down with the same flip-flops. So now it is counting up. When n is 0, it will count up. When n is 1, it will count down. So again I am making n equal to 1. Just check whether it is counting down or not. Yes, so it's counting down. Then 4, then 3, then 2. Yes. So just to confirm, Shubham, are you able to see the counting up and down?
Yes, sir.
So this is a both up as well as down counting. Vishwas, are you able to simulate this thing?
Yes, sir. Doing it.
Vaibhav?
Sir, for D naught, it was 8, na?
For
D0.
D0 it was Q0 bar.
हाँ अपना 8 cell ना sir?
हाँ, 8 in, not 8 cell, it is called as octave.
Octave, okay, sorry, हाँ.
8 cell means it becomes a 8 cell, 8 cell K-map. So
Yes sir.
the K-map is 16 cell, that is 4 variable, and in that you found out the octave. Okay. I'm just stopping this simulation. And the state diagram would be like this. Now you can do one problem at your end, that is this same counter which we did just now, you have to make it lock free. You have to make it lock free. That means the next state of 6 and 7 should be made 0. The next states of 6 and 7 should be made 0 while up counting, and the next states of 6 and 7 should be made 5 while down counting. Again, I am repeating, while up counting, the next states of 6 and 7 should be made 0, and while down counting, when n equal to 1, the next states of 6 and 7 should be made 5. So for m equal to 0, this is the state diagram, 0, 1, 2, 3, 4, 5 in the ascending order. And when m equal to 1, you can see the position of the arrows have changed, or the direction of the arrows have changed. First, the arrows were from like this, from left to right, and when m equal to 1, they are the other way around. So lock free is a homework for you that you will do based on this diagram itself. And now you will design this completely on your own. You will design this completely on your own. So first I will be at 7, then I want to go to 4, then I want to go to 1, then I want to go to 6, then I want to go to 5, then 2, and then again back to 7. So actually you can see the minimum number in the sequence is 1 and the maximum is 7. So we require at least 3 bits to represent the maximum value, that is 7. That is 111. Now, which will be the valid states and which will be the invalid states? So the valid states will be 1, 2, 4, 5, 6, and 7. These are my valid states. And my invalid states would be 0, then 1, 2, 3 is here, 1, 2 is there, 3. 0 and 3 would be my invalid states. Now, this again sequence I have to do it using what? D flip-flop. So step 2, what you can expect here is excitation table of D flip-flop. Excitation table of D flip-flops. Here I have written m equal to 6. Why m is equal to 6? Because my valid states are 6 in number. My valid states are 6 in number. There are 6 valid states, though they are not in order, but there are 6 valid states. 0 and 3 are not there, but total number of valid states are 6 and total number of invalid states are 2. So now I want to count in this sequence 7, 4, 1, 6, 5, 2, 7. So such kind of sequences are used in blinking LEDs. So we have LEDs which we can put, and just by pressing a button the sequence changes. So this kind of things are used there. So let's see. Step number 2 is the same, that is excitation table of D flip-flop. Now let us go to step number 3. So first one is, you can see what I have done is I have listed down the sequence 7, 4, 1, 6, 5, 2. 7, 4, 1, 6, 5, 2 is the sequence. So I have listed down the binaries of 7, 4, 1, 6, 5, 2 in terms of present state. If I am at 7, my next state should be 4. So my sequence is like this, right? If I am at 7, I should go to 4, then 1, then 6, then 5, then 2. And after 2, again I should come back to 7. So the next state of 7 would be 2 or 4. the next state of 1, the next state of 4 would be 1, the next state of 1 would be 6, the next state of 6 would be 5, the next state of 5 would be 2, and the next state of 2 would again be 7. You can see here 0 and 3 states are not defined. So by default, we can consider them as don't care. So we can consider here 0, 0, 0. The next state is don't care, don't care, don't care. And here also we can have don't care. And then we also have 3, that is 0, 1, 1. So that also we can put it as don't care. Not a problem. So please note this table. I will just go through this once. Then I'll again come back to step 3. Don't worry. Then I'll do a calculation of D2. So you can see here that at 0 and 3, which are my invalid states, you can see don't care. You can have chords and K-maps. You can have K-maps for D2, D1, D0. And then this is going to be the final implementation. So coming back to the table, this is what it is. Okay.
So can you please show the question once again?
Yes. This is also a counter, but it is counting 6 states, not up, not down, in some sequence given to you. So by looking at the sequence, you should be able to say which are valid states, which are invalid states. The ones which are not there, they are invalid. And their next states, either you can keep it don't care or you can keep it 0. If they say in the problem, design a synchronous counter for the following sequence using D flip-flop and deal with the lock-free condition, then the next states of the invalid states have to be 0, 0, 0. But if they are not saying anything, you can keep it as don't care. You can save on the design time. So I will be looking only at the logic that you are applying. And even if it is not mentioned in the problem that use lock free, but if somebody designs lock free, that is not wrong. That is also right. So if it is not given, you have two options. You can design lock free counter or you can design the normal counter. But if it is given design lock free, then you have to design lock free. Okay, so I'm showing you the excitation table. We have only 5 minutes remaining. Now you can calculate D2, D1 and D0. So you start calculating it. In the meantime, I will just load the circuit. So I'll just reset it. Now on your screens, you should be able to see some sequence. 1, 5, 2, 7.
Oh,
Sorry? Yes, Vishwas, you want to ask something?
No, sir, it was not me.
Okay. So you can design this. If you want, I can give you the code. So start designing this. Implementation I'll give you, but designing you have to do. So you can see the K-map for this. So for D2, we have two quads, Q2 bar and Q1. So you can just implement this using one OR gate. For D1, in positions 0 and 3 are don't pairs. And we have one pair and one quad. So we should get Q2 bar and Q1, Q0 bar. So this you can implement using one AND and one OR. And finally we have D0. Where we can have like this. So just one quad will do here, and that will give me simply Q0 bar. So D0 is Q. So implementation is simple, but understanding what is asked is crucial. So step number 3 is crucial. So how will you make that table? The sequence which is given to you, simply you will write it in the same order in that table, and then fill the next state table, and from present state and next state based on step number 2, that is the excitation table of the flip flop, we will write the values of D2, D1 and D0. In step number 4, using D2, D1 and D0, we will calculate D2, D1 and D0 using K-maps, and then in step number 5 we will implement this circuit. So this is your step number 5, that is the implementation of the circuit. So just two OR gates and one AND is doing the job for us. And this is D2, D1, right? That's it. So that's it from my side, and please design the lock-free counter for the mode control at your end. Reference circuits are already posted. If there are doubts, you can unmute and ask.